So water and pH. Do you guys remember what the cartoon packet was saying the P and pH stood for? No. It was weird. It's not something I'd heard before this packet. Yeah, power of the hydrogen was what it was saying. But what I'd always been taught was that the P was related to the negative log. P is related to negative log. So it's the negative log of the hydronium ion. I haven't told you that word yet. The H+. I'm going to tell you that word soon. So that is what I've always heard it of as it. I think it's cute that that's what the cartoon called it, but it's really talking about the negative log. So raise your hand if you've used logs before in math. Not like chopping logs for firewood, but logs in math. Okay, good. Another question for you. So let's say we're doing an algebra problem and I want to get rid of addition. What do I do? Subtraction. What about multiplication? I don't want to do that. I want to do division. So with the negative, or with log, what do I have to do to undo log? An exponent, yeah. So it's going to be 10 to the. Those are my two equations that we're going to get today. You're just doing stuff that you've been doing in math before with logs. That's all. And our calculators do all of the hard work for us. We don't have to use log tables. You guys seen those before? Yeah, they're crazy. Like books of log values. So you look up the value and it tells you what the log value of it is. It's crazy. We don't have to do that. We just use our nice little technology. It's fantastic. Let's think about water. So I'm not going to have you pull out the standards because we have such little time today, but this is 8.3 Understanding 4. And it says the self-ionization of water. What that means is when I have a beaker of water, deionized water even, so really purified, doesn't have ions in it, when I have that beaker, some of it's actually going to start reacting with itself. A water molecule is going to hit another water molecule, and it's going to form an acid and a base. And that's going to keep happening in an equilibrium type reaction in my great big beaker all the time on its own because those particles are always moving. And this is my balanced equation. So one water molecule bumps into another water molecule in the right orientation, which steric factors, remember that, right orientation is steric factors, and with the right amount of energy so it overcomes the activation energy. One of them donates a proton. One of them's an acid. It donates a proton, so it becomes an OH1 negative. The other one accepts that proton. It's a base and becomes H3O1 positive. And that equilibrium's going on in my big bottle of deionized water all the time. We don't notice a change though. We did a lab yesterday with distilled water. What was the pH of it? 7. It was neutral. At least it should have been, assuming there were no other contaminants. So it should have been neutral. Well, this, even though this is going on and I've got an acid-base reaction going on all the time in my big bucket of water, it still is going to be neutral overall because I'm forming one acid and one base, one H3O positive and one OH1 negative for each time this reacts. In pure water at room temperature, so this is temperature dependent. So I'm thinking at room temperature, pure water, it's been deionized. I've taken all of the ions that are impure to it out. 1 in every 10 million molecules will dissociate like this. So not a whole lot of it. Okay, they're reacting, just not a whole lot of the particles at any one given time. 1 in every 10 million molecules is going to be involved in this reaction. So I can think of it in terms of concentration. Remember those brackets around it mean concentration. My concentration of my H3O1 positive, and I just used the word without telling you, another word for that is hydronium ion. H3O1 positive, a hydronium ion. The hydronium ion concentration plus the hydroxide ion is equal to the hydroxide ion concentration. And both of those are equal to 1 times 10 to the negative 7. That's because of the 1 in every 10 million. If you were to do 1 divided by 10 million, you'd get 1 times 10 to the negative 7. You're moving the decimal place of the 1 over 7 times, or yeah, to the left. 7 times to the left. Small number. I can think of making an equilibrium equation with this. And this is called KW. It's the dissociation constant. You might want to write that down by the KW. KW means dissociation constant of water. So it is dissociating with the value of 1 times 10 to the negative 14 when I take my hydronium ion concentration and multiply it by my hydroxide ion concentration.
Wait, KW is equal to what?
The dissociation constant.
Of water specifically?
Yeah, yep, that's what the little W is for, water specifically. And again, this is at a set temperature, so this is at room temperature, which in kelvins would be 298 kelvins. Remember, it's not degree Kelvin. Don't do a little degree sign like you do with Celsius and Fahrenheit. It's just a big K, big Kelvin. So this is water on its own, doing this all the time. Overall neutral because they're the same concentration of each of them. Very minuscule amount of it, the concentration of it going on, but this is going on all the time. Then I add other stuff to it and it'll shift one way or the other. So, if I have my H3O plus my OH concentrations equal, then it's neutral. That's what I saw with just pure water, deionized water. If, however, I put something in there and I end up with more hydronium ions, H3O1 positive ions, than I have of my hydroxide, OH1 negative ions, then I'd have an acid. And flip that around, if I have more hydroxide ions, then I have a base. So again, both of those would be I've dissolved something into it. End up with more of one than the other. So that was our understanding 4. Now let's move on to my first equation. So go ahead and put a big star by this one. This is one to memorize. The way that we calculate pH is by taking the negative log of the concentration of the hydronium ion, or the H plus ion. Big star by it. The reason we bother using the pH scale is because those whole numbers between 0 and 14 are much easier for us to comprehend and to write and to deal with than each time saying 1 times 10 to the negative 15 or 4.5 times 10 to the negative 7 or whatever it is. It's much easier using this scale because it's nicer numbers to work with. That's why we do the negative log of each of these concentrations. So that's the why behind it. It's just easier numbers for us to deal with. So the pH is the negative log of the concentration of hydrogen. So here's our first problem. If I have a concentration of hydrogen ions, hydronium ions, equal to 1.0 times 10 to the negative 4 moles over decimeters cubed. Remember, the big M is my concentration. So that's moles over liters, or moles over decimeters cubed, or moles times decimeters to the negative 3. We learned so many different ways of looking at that. I want to know the pH of it. Now you know the equation, but I want to write it down each time I do it anyways. So when you're doing problems, actually write down what you're doing to it. So pH is equal to the negative log of 1.0 times 10 to the negative 4. Excuse me. Thank you. And now we are going to type it into our calculators. And it depends on which calculator you have as to how you will type it in. And I have on the board over here some of the different keystrokes that you will use depending on which of the calculators you have. If you have a TI 30XA, so look at the top. If it's a TI 30XA, this black one on the top is the one that you're going to use. So it would be 1.0, the EE button, for the plus or minus button, log, and then the plus or minus button again. If you have a TI30X2S, you would do the negative sign, it's not subtraction, negative sign log, 1.0, the second, the x to the negative 1 gives you this EE, and then the negative 4. Don't look at these for right now.
That's XS.
X2S.
What does that EE do?
Those are the only two that I have. The EE means times 10 to the something. That's what it means. If you actually try typing times 10 caret and then something, it ends up viewing it very differently and you end up getting the wrong answer. The second should be right there. Yep. Yep. So everybody give it a try. Let's see if we all get the right answer. You can actually show me the answer with your hand.
So once I do the 1.0 to the negative 4, how do I like get out of the
Just if you do log and then the plus minus, that'll give you your answer. If you have a calculator other than those two, you might want to ask somebody around you how to work with your calculator. Okay, so a couple people put their hands up. Let's see if anybody else gets an answer. Nice. Nice. You can make sure you're typing it in so that you can make sure you're getting the right answers. I'm going to show you this one. You guys got it right. 4. Woohoo! It was nice and easy because it was easy numbers. If you know your log scales, you probably would have gotten that one without typing it in. Let's do one, though, that wouldn't be easy to do. My concentration of the H plus ion is now 2.59 times 10 to the negative 11. I want you to figure out the pH. And that's how I would write it again. Let's give them a try. And we'll want to write it in scientific notation so we don't have a number of 0.000, whatever it ends up being. Nicer in scientific notation. Different one than I was thinking. Don't need it in scientific notation. Nice. Okay, saw a bunch of right answers. 10.6. Yeah. Woohoo! If you still didn't get that one because you're still working on your calculators and I haven't gotten around, bless you, to everybody yet, I'm coming around for this next one. So, I want to know the pH if my concentration is 7.11 times 10 to the negative 7. So it'd be negative log of 7.11 times 10 to the negative 7. Give it a try. Call me over if you don't get it. No, so you're good. So the second one is for 7. Yeah. Okay, 6.15-ish, hopefully. Yeah. My sig figs, I didn't do the correct sig figs on that one. I should have had to. Each of those had 3 though, so I used 3 for my sig figs. I got those correct. So the first one really should have been 4.0. Okay, here's an important note for us. If we are increasing the concentration of the H+, we are decreasing the pH. That's an important one to write down or understand, or at least be able to do some quick math in a calculator and figure out the trend. If you've forgotten it, that's always a trick you can do. If it says, how does increasing the H+ concentration affect the pH, just type in a couple of them, see what you get, see what the trend is, and then you'll see that it's a decrease in the pH. It's always a trick you can use. So that's my first big equation, one to memorize. This is my pH scale. I saw it in my notes 2 days ago, 8.3 understanding 3. And this is actually using the colors from the universal indicator. What's another word for alkali? Base, yep, bless you. So I've got neutral at a pH of 7. I get more and more acidic as I go towards 1, and more basic as I go towards 14, which is my purpley color.
So would 14 be a pure acid then?
Base.
A pure base. So
Not necessarily pure, but it's going to be a strong base at the very least. There's going to be a lot of ions of OH in it.
So would it technically be possible to go above that? Could you get a number that you want?
Theoretically, yes. Yes, generally they stick to this. We could go beyond that scale, though, slightly. A lot of the time in problems, you'll get some problems that have ones, but it is theoretical in experimentation to get ones that are beyond either. Okay. So that's the pH scale. I could, however, think of things in POH. So POH, on the next page, is equal to the negative log of the concentration of OH, 1 negative. Again, that P, that cartoon was really cute calling it power, but really it helps us represent the negative log. So I've got my negative log of the concentration of OH. So I can do the same calculations that I did before if I was given the other information. Or I could say, I know because of my KW value, 1 times 10 to the negative 14, that's 14. So my pH plus my POH is equal to 14. So, what was that?
14 minus the pH would equal to pH.
Exactly. So the 14 minus the pH would be POH, or vice versa, depending on what I'm given. So you could be given a problem that has the concentration of OH, and they'd say, what is the pH of it? You would do the negative log, figure out the POH, take 14 minus POH, and you'd have the pH. So that's a possibility. One thing to write down is that this flips the pH scale, or it's flipped of the pH scale. So 7 to 14 would be an acid on the POH scale. And 7 down to 1 on the POH scale is a base. So it's just flipped around.
So which one's flipped?
The POH scale is flipped oppositely of the pH scale. So 1 to 7 would be a base, and 7 to 14 would be an acid. So the problem that we're going to do is starting out with an acid. So it's going to stay an acid. We're going to see what changes with its POH value. But if it's an acid to start with, it's going to stay an acid. So that's another trick for you if you can't remember what happens. Just do the equation. So my pH is 3.2. My POH is something, and I can figure it out based off of the equation. So take a second, do a little bit of algebra, rearrange your equation. Let's figure out what our POH is. And try to remember those sig fig rules from the very beginning of the school year as you're doing it. Okay, 14 is a counting number. So if I have a counting number, do I have to worry about its sig figs at all? No. So I'm just worried about my 3.2. And I am doing subtraction. So which is it? The total number of sig figs, or is it the total number of digits after the decimal when I'm dealing with addition subtraction? Yep, digits after the decimal. Good. So I have 14 minus my pH, 14 minus 3.2. My answer has to have one digit after the decimal because the counting number doesn't matter. So since 3.2 has one digit after the decimal, I have to have one digit in my final answer after the decimal. 10.8. And so we see our scale is just flipped. It's still an acid. It didn't suddenly become a base. It's still an acid. It's just that the pOH scale, anything above 7, is an acid. What questions do you have before we get out of pHs? Question. Okay. So, understandings 1 and 2, we are undoing pH now. So sometimes you'll be given problems where you're given the pH and you're wanting to go back to regular numbers. You might actually take this a step further and say, oh, how much of this was dissolved in the water, so it's looking for grams. We could take it those extra steps as well. We'll do that in tomorrow's practice problems. But for right now, we're just looking for the concentration of it. So if I have a pH of 13 and I want to know the concentration of H+, I'm going to do 10 to the negative 13. And my answer is 1 times 10 to the negative 13. Sorry, I thought it was going to show us what our thing was. Our second sets of key markings over there is what we would do depending on which calculator you have. If you have the TI-30XA, then you're using the one that's in black. If you've got the 2S, you're using the one in blue. If you've got another calculator, I don't know how to use it. Sorry. So, TI-30XA, 1/3 plus or minus second log. The other way is second log negative 1/3. And you should get 1 times 10 to the 13. Okay, let's do a different one. So this one, my pH is 4.5. I want to know what the concentration of H is. Same setup as we did over there. Type it in. Let's see if you get the same thing as me. Give me a thumbs up if you get 3.2 times 10 to the negative 5. Thumbs in the middle if you're still working on it. Thumbs down if you didn't get it.
That, but it gave me the whole number.
It did.
That's,
Scientific notation is always preferred.
but
Yeah.
is there a way to make the calculator do it that way? Or?
Potentially, depending on the calculator. But it's easy just, I don't know off the top of my head. It's easy just to move the decimal. Use those rules from the beginning of the school year. So 3.2 times 10 to the negative 5. I saw a lot of thumbs up. If you didn't get a thumbs up, we'll have some time to work on it in a second. This one is changing just by 1. So it's going from 4.5 to 5.5. I want to know how that's going to change the concentration. So type that one into your calculator. So which part of it stays the same? 3.2 stays the same. My exponent changes though. I have become a 10 to the negative 6. 3.2 times 10 to the negative 6. So our big takeaway from that is that a 1 unit change, so I just went from 4.5 to 5.5, a 1 unit change in pH corresponds to a whole 10-fold change in proton concentration. So if I did a 2 unit change, it'd be 10 times 10, it'd be 100-fold.